So it's my pleasure to present the last speaker of today, Ivan Ip from Hong Kong University of Science and Technology, who will talk about the Casimir actions of parabolic positive representations.
Right, so thank you very much for the introduction, and thanks Hyun and the organizer for the invitation. It's great to be back here again. So today I'll talk about some recent progress related to the so-called parabolic positive representations. So the aim of the research is something called the positive representation of the split real quantum group. So it's UQG with an R here. So just for notational explanation, so UQG is the standard dream field Jimbo type quantum group. So they are generated by the Chevalley generator, EI, FI, KI, with some quantum relationships among them. So the little R here specifies that we want to have certain kind of star structures on this quantum group also. So what we require will be that these generators are self-adjoint. So there are star structure that is anti-linear. So anti-linear. So the generators are self-adjoint, and also the quantum parameter should be specified to be just the complex conjugation. So we require, when we talk about the representations of quantum group with this star structure, what we really want is to find a representation such that these generators act as something self-adjoint on vector space or Hilbert space. Right. So the quantum group relations turns out forces you to have the complex conjugation or the star equals Q inverse, which means that my quantum parameter Q should lie on the unit circle. That's for one. So for convenience, we'll parameterize Q usually by e to the pi I b square. So this b square we will consider to be generic and sitting between 0 and 1. So that Q is not a real unity. Right. And it turns out that if you ever want to have a representation that respects the star structure, then this representation has to be infinite dimensional, except the trivial one. So the main development of this is a project initiated with my advisor, Igor Frankel. So what we have constructed is that so we constructed a representation that we call P lambda. So these generators will act as positive self-adjoint operators. Self-adjoint operators on some Hilbert space, L to R. Right. So these representations are parameterized by lambda. So lambda will be a tuple of, say, non-negative real numbers, n non-negative real numbers. So n, so I forgot. So G we will just focus as the semi-simple type, say over C. Yeah, so n will be the rank of G. Oops. Yeah, so the representations are parameterized by n non-negative numbers, so that these generators act as positive self-adjoint operators on some dense domain. And they are originally constructed through certain kind of quantization of the principal series representation. Principal series. So the principal series representations are modeled over functions of G mod B. So B is the Borel subgroup. So if you think of G as the SLN, then this is like quotient out by the upper triangular matrix. Yeah, so this will be, and actually, in our construction, we will restrict to the totally positive part. So we have some nice coordinate given by loose-sticks data. And then this will be the Hilbert space, where n, the number of the real variables, will be the length of the longest element. Right. So these representations are also irreducible in the sense that any bounded operators strong on the Hilbert space strongly commute with the generators will be scalars. And in particular, we have the center of the quantum group. So these elements sometimes called the Casimirs. So they're generated by C1 up to Cn, the rank of G. So the center of the quantum group under this representation should act like scalars. And the goal is to try to find how these scalars behave, because it's just say in representative theory, whenever you have representations such that the center acts by different scalars, you can distinguish the representations. So they are not equivalent. So these are somehow old. So the, why so heavy? Okay, yeah, so these are sometimes old, and it is based on principal series representation. So it's on G mod B. And the new one, just right here, the new one that we're interested today, the parabolic positive representations, will be based on quantization of the parabolic induction. So instead of L2 of G mod B, we will consider G mod certain parabolic subgroups. So if B is upper triangular, the PJ will be block upper triangular. So this space is a bit smaller. And we can ask the same questions. So how are the generators act? And supposedly they are irreducible, what is the action of the center of the quantum groups? And we will try several different methods to compute these Casimir actions today. Okay, so I need both hands. Right, so this is the overview, and this is our goal of today, is to try to find the Casimir in the case when we talk about parabolic induction. So the starting point of all these projects comes from Teschner around 1999, who studied the non-compact Liouville field theory. So as a byproduct, he has certain representations of the first rank, the SL2R, that we would like to generalize. So the explicit formulas look something like this. Hopefully this is large enough. But this is E. Oh, I missed something. This is E, and then you have F. Okay, so the cut time. So Teschner created this representation. So first of all, it is labeled or parameterized by lambda. So lambda belongs to just single real number because n is 1. And this is supposed to be a dense subspace of L2R. So there are several comments I need to make about these formulas. the first trivial comment is that I over Q minus Q inverse, according to that formula, is just 1/2 sine pi b squared. So this is really just a small positive numbers. So for later convenience, we'll probably just rescale the generators so that I can remove this factor out. So I'll call both E and both F. Just to rescale out that factor so I can erase it. So that's the first comment. All right, so these symbols are really the while operators. So U is multiplication, P is the momentum. Sorry? Small p, B. B is a 0 to 1. Yes. Something is 0 to 1. Right, so my L2 space, the variable I will use U, so because I want to use X for something else. So U is just, this is just multiplication operators, and P is sometimes written as 1/2 pi I, the differential, so that the exponential of P by, say, Taylor's expansion will look like some kind of shifting in the complex world. So, and the notation here, when I combine both U and P in the single exponential, well, we can kind of define this as using the bigger Campbell-Hausdorff formula. So for example, I would just define this as, say, K inverse this. So it's like the while ordering that some talks used before. So either this way or you can flip the two. Right. So these are still on the algebraic level. So the last comment is that if you can look at the action, this is multiplication by something unbounded. And this is shifting in some complex direction. So we expect that these operators are not defined on the whole space, but only defined on certain dense domains. So they are really unbounded operators. So in the study of this theory, we really need to care about the precise domain, how this action acts. The easier go around is to just focus on a particular nice subspace, which we call W. So this will be the span of, say, some rapidly decreasing function that is holomorphic. So A is 0, say. So these are known to be dense in L2R, and all these operators kind of preserve this space. So for the purpose of the calculation in this course, you might just focus on the action acting on W, so that everything makes sense. You have no problems about unboundedness and so on. Right, so this is the representation given by Teschner, and according to our goal to find the action of the Casimir, I can erase this part, it's just for technicality. So the Casimir in UQSL2 can be written, expressed this way. So you can check that this commutes with E and F and K. Or you can also use the standard relation to flip the relation. So these two are the same thing. Right, so this is the Casimir. So if you plug in these expressions into this formula, because the representation is irreducible, you expect this to spit out just a single constant scalar. And indeed, if you just plug this in, acting on some nice test functions, then you will see that this is a very nice positive number, bigger than 2. So that's the result. So this is the SL2 case. And the project with my advisor is to try to generalize Teschner's representation, because this representation is somehow special in the sense that it also admits, say, the braiding operators. We can talk about universal R matrix, but in the sense of Hilbert space, so they now become R operators. So they are unitary operator instead of matrix, but it still satisfies the Yang-Buster. And there's also the tensor product decomposition and the Peter-Wiles theorem, for example, that is okay when at least working in type A. So on that board, that Hyun-Kyung complaint I'm writing too small is the example for UQSL3. So you can see that the expressions, even though it's kind of complicated, are still expressed in terms of these position momentum operators. So in UQSL3, the length of the longest word is 3, so it acts on L2R3. And I just labeled the variable by UVW. So this will be the expressions for L2R3. And you can see that these are all polynomials in those while operators, the exponential to position and exponential to momentum. And you can check that all the relations of the quantum groups are satisfied, at least when you act on dense subspace like this.
The Casimir?
Sorry? This is the Casimir. Yeah, Casimir. Sorry. Sure. Thanks. Yeah, for Smoot can work on that. You can set to this is one of the, they call it strange representation in Smoot's classification. It's not like the standard. There are like 8 families. This is one of them. Yes. Yes.
Why is B squared not allowed to be bigger than 1?
That is a very deep question, actually. That's a very deep question when you want to understand when this dense subspace is a core of the self-adjoint operators. When B is bigger than 1, you get some trouble. this B is not that big, so I should use some other symbols. Yeah, so when B is between 0 and 1, W will be the core of this self-adjoint operator, a symmetric operator. So they have a unique extension as a self-adjoint operator. But when B is bigger than 1, Rushina's results causes some trouble. Yes. Sorry? Oh, we just don't want root of unity for now. We don't want root of unity. Why we don't want root of unity? That's a good question. But we, probably I can try to say something at the end. Probably. Okay. Yes. Yeah, so this is the analytic side. We have these formulas, which is kind of ad hoc, but they all comes from attempts to quantizing the principal series representation. So the new development comes when cluster algebra came, and we found out that we can realize these representations using quantum cluster algebra. So for cluster realization, we have the following embedding, which I'll explain. Yeah, so DQ here is the Dreamfield double of the Borel part. And for our purpose, it really just looks like generated by EFK, the quantum group, and one more extra generator K prime that looks like K inverse, so that you can recover UQG by quotienting out the K prime. Actually, it should be B, but the Borel part of quantum group. So I mean, and there are the index. Right. So the left-hand side is the quantum group. The right-hand side is some quantum cluster algebra. So it's the upper quantum cluster X variety, X algebra. And they are associated, they are kind of first discussed by Fogg and Goncharov and Goncharov-Schoen. I'll just put Schoen here. So this is certain kind of quantization of the cluster X variety of the framed local G local system on marked surface. And for our purpose, the surface we are looking at will be a punctured surface with 2 marked points and a triangulation on it. So Fogg and Goncharov or Schoen, so they discussed the cluster structure of this framed G local system. So the cluster structure are encoded by certain quiver on this surface, on the triangulation of this surface. So in the case of type A SLN, the quiver is actually quite easy to draw. So it is just the N triangulation quiver. So with some arrows accordingly. Just skip drawing. And we will use the version where they allowed arrows between frozen variables. So the boundaries are the frozen variables. So this quiver encoded the cluster X variety, and the quantization of this will be the quantum cluster algebra. And we would like to only look at the upper one, which means that they are Laurent polynomial in every seed. So you have quivers, you can mutate. If you mutate, then you get another torus algebra. So here, this is the X version, not the A version. So it corresponds to the coefficient rule. So in general, the Laurent phenomenon is not satisfied. So this is strictly smaller, usually. But it turns out that there is an embedding of the quantum group into this OQX, and there are even polynomials. So all the generators will look like polynomial in the cluster variables. So how do you read the relationship? So let's say if you have an arrow between 2 nodes, so each node corresponds to 1 cluster variables, then you just require the index 1 and index 2 to be Q commuting. Right. So this quiver kind of describes the Q commutation relationship among the cluster variables. And when you do cluster mutations, you get a different quiver, different algebras, but you still have the polynomial embedding. So the quantum group actually sits inside the upper algebra. Yeah, so this is for one triangle. So you can expect to get the punctured disk version. I just have to set 2 copies and then glue them together. And what you get will be the picture on the right of this board. So that quiver will be describing the OQG. So as an example, if I want to write down the expression of E1, for example, or the rescaled version, what I need to do is just to look for a certain path on my quiver, and then write down this as a telescopic sum. So it's like x1, x2, x1, x2, x3, and so on. So this 1, 2, 3, 4, 5, there should be six terms at the end. Yeah, so there's a kind of an algorithm telling you what exactly is this embedding. So how is this related to the positive representations? Well, because these are just quantum torus algebra, it is very easy to write down a representation of it. So we call this the polarization. So the polarization really is just assigning each cluster variables to be exponential of something self-adjoint such that they satisfy the appropriate commutation relation. So this is the adjacency matrix of the quiver. Oh yeah, by the way, so all I draw here is just simple lace, but it works for non-simple lace also with some scaling. Right, so this will be self-adjoint thing acting on some Hilbert space. Again, the previous comment, there should be something unbounded. And so this X will be realized by, as you can tell, some combinations of U, P, and the parameter lambda. So there's some linear combinations of UP lambda such that the Q commutation relation of them are satisfied on the Hilbert space. Yeah, so once you have such choice of polarization that is irreducible, so that centers irreducible, so that the center of the cluster algebra acts as scalar, then it turns out that the scalar uniquely determined the representation. So representation with the same action of the center will be unitary equivalent. And also the cluster algebra itself has a mutation formula, and the mutation will correspond to a unitary transformation on the Hilbert space by the quantum logarithm. But we are not going to discuss in detail there. So now, if I have an expression of my quantum group in terms of the cluster variables, I assign each xi to be the exponential, then the pullback to the quantum group will become expression like this. So it completely recovers the positive representation that we discovered earlier on without using the cluster algebras. Yes?
In some unbounded operators well defined.
We need to extend the domain, but they are at least well defined on W. The sum is well defined on W. Because the sum of two, I mean, in this form, the sum, each term preserves W, so the sum also preserves W. And W is a dense subspace. So as I said, that's why we require B to be less than 1, so that all this extension makes sense. Sorry?
About the difference of two unbounded.
So we never have, we don't have difference here. They're all positive expressions because these are embedded into the upper cluster algebra as positive polynomials. So all the cluster mutation formulas are all positive. I mean subtraction free. Yeah, so the OQ acts on Hilbert space. So the pullback of this will give you a representation of the Dreamfield double acting on the same Hilbert space. And if you find a polarization such that the KK prime equals 1, then you get back a representation of UQ. So that's the standard representation. Oh yeah. An assignment of how each cluster variable acts on the Hilbert space. Yeah, so this quiver is not unique, definitely. You can do mutations and change to other quivers. So this kind of standard, very symmetric version actually corresponds to the longest word. So for example, you can see in SL4, there's something like 1, 2, 1, 3, 2, 1. So it's kind of assigned to a longest word. I mean, the reduced word of the longest element. So how about the parabolic that we are interested in today? So as I mentioned, we will try to model this on the parabolic induction. So we will index the parabolic subgroup by J. So this I is the thinking index. And we choose a subset of the I. So in particular, when J is the empty set, then we just recover the standard representation. So we can split the longest word into two parts easily. So the part that involves only the index in J and the rest of the part. So as a quick example, if SL3 and SL4, then let me use I for the word. So let's say you usually 1, 2, 1, 3, 2, 1. So this part will be the J part, and this part will be the bar part. So you can always split a longest word by pushing the sub-index in onto one side. And now the observation is that, as I mentioned, this basic quiver that Gontrovsky and me constructed depends on the choice of longest word, and they are actually amalgamation of these two components. So you have the 1 to 1 on the left, 1 to 3 on the right. So the idea of or the construction of the parabolic positive representation turns out to be just truncate out the J part. So as an example on the board here, this is the picture for SL4, and you can kind of identify a SL3 part in the middle. So it's like a one rank smaller hexagon in the middle. So by truncating this out, we just kind of remove this portion and then reglue the corresponding vertex together. The end result will be this quiver. So you just completely remove the thing in the middle and squeeze things back together. And the amazing thing is that after we do this, we do have a representation of the string double into the cluster algebra corresponding to this truncated quiver. And so in particular, if you choose a polarization of this cluster, you get a representation of the quantum group that is different from the one that I did with Franco before. And that is the parabolic positive representation. Yeah, so just some further details. So this parabolic positive representations is still regular in the sense that we still have a map from the trivial double to this upper cluster algebra. So in particular, all the generators are universally polynomial. So no matter what quantum cluster mutation you do, you get a bunch of rational expressions. The generators still looks like polynomial. So they are nice ones. And in particular, a polarization. So a choice of action of the cluster variables of this will induce these parabolic representations where this time we need less parameters. So the number of parameters is I minus j. And also one funny thing that I found is that this time you have to consider also the negative parameters. So previously in the Franco construction, the representation depends on lambda that is only non-negative. So if you use a negative lambda, you can always use some transformation to get it back to the positive ones, but not for the parabolic case. So you need to take care into account also the negative parameters. That is something kind of new. Yeah, and these actions are on L2R of the size of that, which is the length of this W bar. So it's smaller. Yeah, so in particular, in SLN, we have some special case. So this, I call this the minimal parabolic because it can act on just L to Rn. And only parameterized by a single number. So minimal in the sense that this is like the smallest dimension you have. Right, so the goal, as we explained, is to try to compute how the center of the quantum group acts on every parabolic representations. Yeah, so the goal, compute is for every k, every j, and every g, every type. Which I originally does not expect to be able to be done, but then in the joint work with my students, somehow we have some progress. So the first way is the stupid way, is just to use brute force. So let's just look at Teschner's expression again. So in this case, the triangulation is very simple. I mean, the quiver is very simple. You just have one triangle as a quiver. Like this. So when you glue, you get this quiver. So the middle one cancels. I mean, we don't allow 2 cycles on quivers, so it cancels. So let's label them. Right. So then, as explained, we have a realization of the quantum group generator using cluster variables. And they are very neatly computed. It's a trivial double, so you also want the other one. So this is the expression. And you can hopefully see that if I choose the polarization of these cluster variables appropriately, I will recover what Teschner wrote down there. So this quiver has 2 kind of, the center is generated by 2 things. So the center is x2, x4, and also x1, x3. So these 2 are the center. So if you want to have an irreducible polarization, you better want these 2 to act as scalars. But we remember, to get back to a representation of UQ, we require kk prime equals 1. So we require something like x1, x2, x3, x3, x4, x1 with some appropriate q, which I think is 1. Is 1. So we require this relation also. Yeah, so you only really have one degree of freedom. So when you assign a polarization, my version is to put a 4 lambda here and minus 2 lambda here. So that's kind of my assignment. So you can see the minus 2 lambda appears in F somewhere. Yeah. And then x3, x4 has plus 2 lambda, which is this first. Yeah, so what is the Casimir? The Casimir is EF minus QK minus Q minus K inverse. If you just plug in this thing back, then algebraically you will get x1, x2, x3, x4. Probably this. So you get this expression, which is obviously in the center. Right, and also just from the polarization you can see that x1, x3 gives you minus 2, and this product gives you plus 2 lambda. So you recover the previous expression. So for SL2, it's easy enough. But how about higher rank? So in general, there's a formula telling you the generator of the center. So it's generalized Casimir. So it has a formula that looks something like this. So you have the universal R matrix restricted to the K fundamental representation. You get a matrix, then you take the some kind of quantum trace, you get an expression in terms of the generators of quantum groups, but you need to allow some fractional powers of the Cartan generators. So H will be the cos theta number. Yeah, so in general, there is this formula, and geometrically, there's a meaning here as the monodromy around the puncture of the cluster structure. So the embedding of the quantum group will lie in the center. So in particular, this expression should give us a scalar action. So just to give an example, and you'll see things becomes quite annoying. Something like that. So yeah, so you need some fractional powers, and you also require the use of the Lushtek's automorphism. So this is something like E1 E2 minus E2 E1 divided by QQ inverse, and then you have some scaling here and there. Yeah. But in any case, this is an expression in terms of EF, and some fractional powers of K. And because SL3 is kind of symmetric on both indexes, the second Casimir is just the first one with all the index flipped. So we just need to take care of one. Yeah, so how does this act? Well, you can write this using the cluster realization in terms of cluster variables, or you can just directly plug in this huge formula into this huge formula in Mathematica, and things just cancels. You spit out one single number. And the number is, you might recognize, it's just a symmetric polynomial on the root. On the roots. So with this first one, so it is a symmetric polynomials in the root lattice, and it's something positive. It's bigger than 3. So this is our standard one. You can also plug this in the minimal parabolic, for example, and you will expect to get another numbers. So let's say J is the minimal parabolic. And you get some negative numbers, actually. And the question now is, can we really obtain this in a more systematic way, rather than just every time plugging in this very huge expression into a very huge expression and do simplifications? So first of all, this is the action of the Casimir in the standard case is kind of well known. Or no, not well known. So it can be done by some kind of wild character formula. As you can tell, it really is like the sum of the exponential of the weights. So you kind of expect that, and we can prove that. So whether we can specialize these formulas to get back the action in the parabolic case or maybe other cases. So that comes the second way, is to use the so-called virtual highest weight. I mean, these are representations on L2R, so you really don't expect there are functions so that the generators are queued. So that's why we call it virtual, because our idea is that if you look at the expression of the Casimir, you can always write in such a way that you have the K part, the Cartan part, and also some part that ends in E or F. I mean, you can flip the two. So if somehow I have a function that the E queues, which looks like a highest weight vector, then I can just compute the action of C by looking just on the Cartan part, and the Cartan part is kind of symmetric, and you can kind of tell from the expression of the numbers and the expression of the case. So it turns out that these will be expressed in terms of some delta function laws. Because we know these expressions algebraically will all cancel and get a number. Even though originally it is defined on this dense subspace W, it does make sense when you talk about functions that work formally. So no matter what it do to the functions, delta functional or not, the expression should still be a number because they are number by default. So if I formally act these operators on a delta functional in such a way that this E, the generator, kills it, then we can get the number by just looking at how the K acts on this delta functional. Yeah, so the kind of funny thing is that we require the argument to be complex. So just to give an example, so let's again look at Teschner's expression over there. So if I want to kill E, for example, I can first factorize the minus 2p out. And then the remaining thing will be something like this expression. Yeah, so if I act on this, it will be 0 if alpha k is chosen to be this magic number. And this is also where somehow the modulatable thing shows up. Yeah, so if you formally treat this as a multiplication on a delta distributional, then it means you are substituting U with alpha, and then this whole thing just becomes 0. So if you take this delta, then the first term of the Casimir cancels, and K will act as some expression I didn't write down. Yeah, I didn't write down. Yeah, so K will act as some kind of numbers, probably on 5. And combining, you will get the Q and Q inverse cancelled. You'll get back this expression. And this can be also done on the minimal parabolic. So this time you have more variables, and you will choose. So let's call this magic constant CB. So if you choose this as our specification, then again, this will be the highest weight, and you can compute, let's say, the first Casimir to be of this form. Where T is number. And you can also have formulas for the rest of the Casimirs. So this already or originally done because the minimal parabolic corresponds to that picture. So each generator is just two terms. Each generator are just two cluster monomials summed together. So it is relatively easy to solve what alpha I need to kill the E. So originally, I think this is kind of a hard question to solve for the highest weight for arbitrary parabolic. So I asked my student to do it, and it tells me that he has a general way to compute this for all types. So it's kind of a bit unexpected. But in any case, I can write down how many minutes I left.
8 minutes.
Okay, good. So it's a joint work with my student Liuichi. Man, he's a Japanese-Chinese mix. So yeah, our work shows that we can compute for all types and all parabolics. So in type A, say to compute the first Casimir, we first just take the standard one. So the standard one we know are the symmetric function. Just like the formulas. Oops, I erased. Yeah, so the standard expression are the symmetric functions. And we just set all the lambda to 0 whenever the index lies in your J. And then we just combine same term. Right after you do this specification, some terms are the same. So you combine them. And in case they appear n times, you just replace the constant n by a quantum number this way. So you combine the same term, and if there are more than two terms that looks the same, then you replace the coefficient by some quantum numbers. So it turns out that this is enough to compute all the expressions of the Casimir in type A. And for other types, unfortunately, this has to do case by case modification. Mainly based on how the index J relative to the branch point of these thinking diagrams. Yeah. So this is for C1, and CK can be obtained from C1 by some generating functions. So you can find some explicit polynomials such that the action of CK can be read off from some coefficient of that polynomial. Yeah, so this is like a answer to our original question, what is the action, but it somehow lacked this universal explanation why this is true, and we need some kind of case-by-case study. So we would like to have some more universal explanation how to compute these things. And so here comes the second, or the last approach. So this is with Gus Schroeder. And we try to realize the parabolic version as some kind of quantum Hamiltonian reduction. So just to have a very brief review. So classically, a Hamiltonian reduction, the setup is like you have a moment map from a Poisson manifold, and there are two versions, either to the Lie algebra or to the Poisson dual of a Lie group. So we'll use the group version, and then try to consider the geometric quotient of the inverse image of 0. So something like that. I'm not a geometry person, so hopefully I didn't say anything nonsense. So you can talk about the dual. So the dual will be functions on G star to functions on M. And this allows for quantization. So the quantum version, probably due to Etinghoff, at least I learned this from his paper, is that the quantum version of the Lie-Poisson dual will be the quantum group. And the algebra here should be our quantum cluster algebra. So this is like the Hopf algebra, is the algebra. And we would like to understand the parabolic version as some kind of invariant subspace of the quotient of some ideals. So this is like the general setup. So I is some ideal in the quantum group, and this action is some kind of conjugation action. Yeah, so we would like to realize the parabolic version as some kind of quantum Hamiltonian reduction. Sorry? Poisson manifold in classical case, just Poisson manifold. Right, but I didn't find this data is kind of hard. So actually this is maybe I use this side. This is better probably. Yeah, so instead, so right now we have something like the group embedding in the standard one, and also on the parabolic one. And instead of looking at the algebra directly, we just try to consider their action. And try to realize the smaller space as some kind of invariant subspace of the bigger one, but somehow spanned by invariant subspace, spanned by this complex delta distribution. So if you look at Teschner's work again, so it turns out that all we need to understand the case when j equals I. So we basically kill everything. So we just need to understand on what kind of one-dimensional space spanned by the delta distributional such that the quantum group action becomes trivial. So in the tensionless case, it's very simple. We can try to see how we can adjust the parameter in such a way that they become a trivial representation. So in tensionless case, I can again choose this magic constant as my specification. So we have just computed that E acts as 0 and K acts as, I actually write here. Right. So now if I further set lambda to be minus CB, so if I set this, then this becomes 1. So you can compute this actually 1. So K also acts trivially. And it turns out that in this case, F also acts trivially. So this becomes a trivial representation. So if you do this, then for example, you can easily see that the Casimir in this case is minus Q inverse, because K just add by 1, F add by 0, K add by 1, so you get this quite quickly. So now I don't need this anymore, and I have 0 minutes left. So let me just write down the theorem and call it that day. Yeah, so hopefully by this year. So what we have is that we can obtain the trivial representation from the standard one by evaluating on some special form of virtual highest weight. So this implies that each E generated at a 0. And then we further set all the parameters to be this magic constant. And this will ensure that the K at S1. And the non-trivial part is actually to see that this 2 actually is enough to imply that the F generator also add by 0. So this becomes the trivial representation. And to obtain the general parabolic representation, you simply set the corresponding sub-representation of the, I don't know how to call it, G of J, like the parabolic one, to the trivial, and then somehow reset the generators. So, which has to erase things. So for example, this is the SL3, and if you look closely, you can identify a SL2 representation inside. So this is like a SL2 representation. So our idea is that if we specify to certain highest weight, then this will cancel. The whole time gone is 0. This will be 0. And then the W's are also set to constant. Lambda is reset to constant, so they're all cancels. And this will cancels. And all you are left with are the 2 terms, which is the minimal parabolic representations. So you recover the minimal parabolic by restricting appropriately to some delta functionals. So of course, I mean, this is still a bit heuristic. So the future work is to try to make these things more rigorous in the appropriate sense that actually matches the actual quantum Hamiltonian reduction. Like we should consider some Galvan triple, the core, the W space, L2, and then the distributions. But the more important part is that the standard representation is around a puncture of the G local system. So it gives a local model how the cluster structure works. And so this reduction can help, say, discover cluster structure for certain reduction where the monodromies around the punctures are not Borel anymore, but some specific conjugacy class. So that should be worked on like general marked surface. So yeah, I will stop here. Thank you.
Thank you.